Okay. Yeah. Thank you very much for the introduction, and I would like to thank the organizers for inviting me to this wonderful conference. So today I'd like to talk about our recent result about channel resolvability construction using multiplicative weight update algorithm. So this is a joint work with my student, Koki Takahashi, from my university. So this talk is about channel resolvability. This problem we have seen yesterday in the talk by Li Gao, but let me start with some background on this problem. So channel resolvability is a kind of random number simulation problem through noisy channel. And some version of this problem can be traced back to Weiner's paper in 1975. And his version of this problem is called, in modern terminology, soft covering, introduced by Kaff. And the terminology of channel resolvability was introduced by paper Han and Verdu. And they introduced this problem as a converse proof method for identification via channel. I'm going to explain more detail about this connection later. And this channel resolvability problem is a kind of a dual problem to channel coding problem, and it was a starting point for Han and Verdu to develop information spectrum method. And this channel resolvability problem has various applications. One famous application is that we can use this technique to construct wiretap channel coding or channel simulation problem, etc. So this problem is quite important problem, and it has been studied quite a lot. But existing proofs of this channel resolvability are via random coding method. Next, let me explain some background on multiplicative weight update, MWU algorithm. This algorithm is not well known in information theory community. If you are working on learning theory, you may have heard about this algorithm. But yeah, this algorithm is quite well known in theoretical computer science community. And this MWU algorithm is a kind of meta algorithm for various problems. For instance, it can be used to prove minimax theorem in game theory, or it can be regarded as an abstraction of the famous boosting algorithm in learning theory. And also, it can be used to prove something called Impagliazzo's hardcore lemma in complexity theory. And also, it is related to exponential gradient algorithm in optimization theory. And this MWU algorithm can be used to derandomize certain proofs. For instance, this Impagliazzo's hardcore lemma in computational theory, this is one of important lemma in when we prove hardness amplification in computational theory. And this lemma, for instance, we can prove this lemma by combining minimax theorem and Chernoff bound. So we can prove this lemma using a probabilistic method, but also we can prove Impagliazzo's hardcore lemma using MWU algorithm. In fact, Impagliazzo's original proof is kind of deterministic proof, and so this MWU algorithm can be regarded as an abstraction of Impagliazzo's original proof. And also another example is a hypergraph covering or quantum hypergraph covering. So this quantum hypergraph covering was introduced by Alswede and Andreas Winter in their paper about identification, quantum identification via channel, and it is closely related to channel resolvability. And in their paper, they proved they solved this problem using a matrix version of Chernoff bound. But more recently, Kale revisited this problem by using MWU algorithm, a matrix version of MWU algorithm, and he provided a deterministic solution for this problem. And in fact, our work is inspired by this result. Next, let me explain our motivation of this work. In the channel coding problem, the standard channel coding problem, there are basically two approaches, two proof approaches. First one is the famous Shannon's random coding method. This method is widely used in information theory, and it is written in any textbook on information theory, such as Cooper-Thomas. Another proof method is known as Feinstein's maximal code construction, and this proof method is, unlike random coding, it is deterministic. Feinstein's maximal code construction is less known compared to random coding method, but it is quite important. And for instance, it is written in Chisar-Kellner textbook or Wolfowitz textbook, and yeah, it is. Yeah, so some people know this, and even for quantum setting, classical quantum channel coding theorem has been proved using maximal code construction by, for instance, Andreas Winter's paper or Ogawa Nagaoka's paper. So it's quite important, and yeah, through this method, we can understand the channel coding better. As I said, channel resolvability is a kind of a dual problem to channel coding, but as I said, existing proofs are based on random coding. So to understand channel coding, channel resolvability better, it is desired to have a deterministic proof for this problem as well. And also, another motivation is identification. As I said, channel resolvability is a proof method for identification via channel, and there are several open problems for identification via channel, such as identification via broadcast channel. So better understanding of channel resolvability might be helpful to tackle some open problem in identification. So this is the outline of the talk. So first, I'm going to explain more detail about the MWU algorithm. And then I'm going to explain channel resolvability setup and also connection to identification and wiretap channel briefly. And then first, I'm going to explain proof of channel resolvability using random coding and Chernoff bound. Then I will explain our proof of channel resolvability using MWU algorithm, and I'll finish the talk with some conclusions. Okay, so the problem setting of MWU algorithm is the following. So we consider two-player game. So first we have X player, and this X player would like to maximize a game. And another player is which we call Y player, and Y player would like to minimize a cost. And cost and gain are given as m of xy, which takes a value between 0 and 1 for X player's input X and Y player's input Y. Okay, so this is the setup. And we consider L rounds game. And in each round L, first, Y player select some strategy. Y player select some mixed strategy, FL, which is some distribution on alphabet Y. Then, after that, X player responds with some deterministic strategy, XL, from alphabet X. Okay. And they play this game L rounds. And our goal is to construct a sequence of Y players' strategy, F1 through FL, such that the average cost is not too much more than the cost of Y players' best strategy in hindsight, which is given by this. So this is average cost. So we play L rounds, and in each round, Y player select YL according to this distribution FL. So we take expectation. And this is a hypothetical situation. And Y player observing X1 through XL select best strategy. Okay. And we want this quantity to be not too much more than this quantity. That's our goal. And the question is how we choose F1 through FL. And MWU algorithm provide one solution for this. So MWU algorithm is some iterative algorithm to select a Y player's mixed strategy. So we are given some parameter, error parameter epsilon. And first, we set this weight vector, initial weight vector W1 to be all 1. And then for each round, L equal 1 through L, first we set FL to be the normalized version of this weight vector. Here, this phi L is the normalization constant. This is just summation. And then for given X player's response, XL, we update the weight vector. So updated weight vector, WL plus 1, is we have a previous weight vector, WL, and we multiply exponential of minus epsilon times this cost mxy. Okay. So we multiply this, and this is why we call this multiplicative weight update algorithm. The algorithm is quite simple. And this algorithm has the following guarantee. For given error parameter epsilon, the mixed strategies F1 through FL selected by MWU algorithm satisfies this bound. The left-hand side is 1 minus epsilon times the average cost of Y player. And on the other hand, right-hand side is the cost of Y player's best strategy in hindsight plus some error term. And if epsilon is very small and if L is sufficiently large, this term will be very small and this will be almost 1. So we can get our goal. So this is from Y player's viewpoint. And from X player's viewpoint, we can consider the following game. We consider just one round game such that X player first uses mixed strategy such that the probability of symbol X, small x, is given like this empirical distribution. Frequency of symbol X that frequency of symbol X that occur in this sequence X1 through XL. And then Y player responds with the best strategy. Okay. Then X player's gain will be this term. And then this bound, another interpretation of this bound is that X players' gain is almost as large as average gain. Average gain of L rounds game played against F1 through FL selected by MWU algorithm. And later in application, we will use this interpretation. Okay, so this proof of the performance guarantee of MWU algorithm is not too complicated, so I'm going to explain some proof here. So we use some basic elementary inequality. E to the power minus theta can be bounded like this, 1 minus theta plus theta square for theta in this range. And this is also basic inequality. 1 plus theta is bounded by e to the power theta. And first thing we need to do is evaluate this normalization factor. Normalization factor is by definition summation of weights W L plus 1. And by the definition of update rule, WL plus 1 is WL times this exponential minus epsilon mxy. And if we divide weight vector by phi L, we get this distribution FL. And by using this inequality, this part can be bounded like this. Then again, by using this inequality, furthermore, this can be bounded like this. Okay, very simple manipulations. And by using this manipulation, phi L become phi L plus 1 become phi L plus times something. So by applying this manipulation inductively, phi large capital L plus 1 can be bounded by phi 1 times something like this. And phi 1 is initial vector is all 1, so it's phi 1 will be cardinality of y. On the other hand, phi L plus 1 can be lower bounded by W L plus 1 for any y, which is given by this. So by combining this and this, we get some bound like this. And finally, here we have cost square, but cost is in this range, so cost square is less than cost itself. So by moving this guy to the left-hand side, we can get the desired bound. Okay, next let me briefly explain some variations of MWU algorithm. In the previous version of MWU algorithm, the mixed strategy FL can be any distribution on alphabet Y. But in a modified version, we can pick Y player's strategy to be included in some convex set C inside the distribution set. And this kind of version is useful in certain application. Another variation is matrix version of the multiplicative weight update algorithm, which might be interesting for this audience, I think. So in the matrix version, X player's strategy will be classical symbol X. But Y player's strategy will be some density matrix rho in some Hilbert space. And cost will be a cost matrix, positive semi-definite matrix MX between zero matrix and identity. And then in the matrix MW algorithm, we update, we find for initial weight will be initial weight matrix will be identity, and then we update weight like this exponentiation of matrix, and we update in a similar manner as the previous MW algorithm, and we have also similar guarantee like this. So average cost is bounded by the cost of y player's best strategy in hindsight plus some error term. And here, this V can be any pure state in this. And the flow of the proof is quite similar to the MWU, but we use, for instance, Golden-Thompson inequality, etc. Okay, now let me explain the problem setting of channel resolvability. So we are given noisy channel W with input X and output Y. And for input distribution P, our goal is to simulate the output distribution WP defined by this formula. To simulate this output distribution, we construct a channel resolvability code, which is given by L tuple of input symbols. And for a given channel resolvability code, we can define this output distribution WC, which is the average of WXL for these guys. And then we evaluate the approximation error by using the total variation distance. And we want to make the size of the code, size L, to be as small as possible. That's our goal. And for discrete memoryless channel Wn, we are interested in the minimum rate. So the size Ln grows with n, and we are interested in the growth rate n, 1 over n log Ln. And as we have seen in yesterday's talk, for IID input distribution Pn, the minimum rate is given by the essentially by the mutual information, but there might exist multiple p prime that such that output distribution coincides with WP, so we minimize over those distributions. And for general input Pn that may not be IID, the worst case minimum rate is given by the Shannon capacity. Next, let me explain some implications of this channel resolvability. First implication is identification via channel introduced by Alsfede and Duke. So in this problem, we are given noisy channel W with input X and output Y. And the sender has some message I, and encode this message I into input symbol X. But here, sender uses stochastic encoder. So for message I, we assign probability distribution Pi on input symbol. Then we are given some output distribution induced by this input distribution Pi. And by observing output symbol distributed according to this distribution, the receiver's goal is to decide whether the sender's message I coincide with receiver's message J. So it's different from a message transmission problem. The receiver is only interested in this checking this equality. Okay, so it's much easier task than the transmitting message. And for received signal, if received signal is included in acceptance region DJ, the receiver accepts as I and J coincide. Otherwise, the receiver reject. And so this is like a hypothesis testing problem. So we have multiple hypotheses, and the receiver decide hypothesis through noisy channel. And we can define type 1 error probability and type 2 error probability for this problem. And for discrete memoryless channel setting, for the standard channel coding problem, if we use channel n times and capacity is C, we can send NC bit message. That means the size of message is 2 to the power NC, single exponential. But quite surprisingly, for this identification problem, we can identify message of doubly exponential size. And doubly exponential optimal message, optimal doubly exponential rate is given by Shannon capacity again. But proving this result is quite difficult, and Han Verdu introduced channel resolvability problem to prove converse for this result in their paper. And they showed that by using channel resolvability, we can focus on something called L-type. L-type is probability distribution such that each probability is integer multiple of 1 over L. And so for identification code, for each message, we can use any distribution PI. We have too much freedom, but for given PI, by using channel resolvability, we can replace this PI with L-type with small error, additional error. And then we can only consider identification code such that every PI is L-type. And then the converse can be done because the number of L-type can be bounded by some counting argument. Another implication of channel resolvability is wiretap channel. So wiretap channel is some security problem in information theory introduced by Renner and further studied by Kellner. And channel resolvability can be used for code construction of this problem, and it has been used in many papers initiated by and also Hayashi, and for quantum setting, Devtak, Winter-Yang, and etc. And so we have some noisy channel with one input and 2 output. And one of input is observed by some wiretapper. And the sender wants to send message through this channel and send this message to the receiver reliably. And also, the sender does not want to leak this message to the wiretapper who observes Zn. And in the code construction of this wiretap channel, roughly for each message, we construct channel resolvability code so that output distribution of wiretapper will be close to some target distribution that does not depend on the message. So no matter which message sender sends, wiretapper observe Zn that is distributed according to the same target distribution and cannot get any information. That's the rough idea why this channel resolvability is useful for wiretap channel. Okay, so next let me explain the random code construction of channel resolvability. So for given input distribution P, in the random code construction, we independently generate L symbols x1 through xl according to distribution P. And for this random code generation, we can evaluate the performance in various ways. For instance, one way is to evaluate ensemble average of approximation error by using information spectrum approach. So in this approach, we total variation distance is essentially L1 distance. So we switch L1 distance to L2 distance by using Cauchy-Schwarz inequality, and then we can bound L2 distance by a kind of similar manner as evaluation of variance. Such an approach has been used in some papers, and alternatively, we can also evaluate approximation error using Chernoff bound, which was used by Alswede for classical case and Alswede-Winter for quantum case. Let me explain this approach in more detail next. So for that purpose, let me review Chernoff bound. So we consider the following version of Chernoff bound. We have a random variable g1 through gn IID, and each gl takes a value between 0 and 1, and the expectation is mu. Then the probability such that the empirical average deviates from expectation by the factor epsilon mu can be bounded exponentially, and exponent is roughly given by minus epsilon square L times mu. There are various versions of Chernoff bound. This version of Chernoff bound is useful when the expectation mu is quite small. Okay, then by using Chernoff bound, we can evaluate the performance of random coding. In order to focus on the core idea, we only derive suboptimal bound. To derive optimal bound, we need to add more argument regarding smoothing. I'll come back to this smoothing at the end. So first, let d max be a maximum of this log likelihood ratio between Wx and Wp. Then this random variable, here x is random variable, and this random variable Wxy over Wpy times e to the power minus d max. This random variable takes a value between 0 and 1. And also, the expectation of this random variable with respect to this distribution p is given by e to the power minus d max. So we can apply the Chernoff bound for the sequence of this random variable. And we apply Chernoff bound and also union bound. Then probability such that this empirical average deviate from e to the minus d max, which is the mean of this guy, by the factor of epsilon times e to the power minus d max, can be bounded exponentially like this. Okay? And if the right-hand side is less than 1, which is true if log L is larger than d max plus something, then there exists a code x1 through xl such that this deviation event never occurs. And this deviation event can be, we can rewrite this deviation event like this for every y. And from this bound, we can easily bound the total variation distance. So this is how we evaluate the performance of random coding using Chernoff bound. Okay, now let me explain our proof of channel resolvability using MWU algorithm. So here we consider the following channel resolvability game. So our cost is mxy is this ratio mxy over wxy over wpy times e to the power minus d max. And this cost takes a value between 0 and 1. And then in each round, first, Y player selects mixed strategy FL by MWU algorithm. And then X player responds with XL, which is given by argmax of this average cost with respect to FL. And we can verify that this max of this average cost with respect to FL is as large as e to the power minus d max. And this can be easily verified because this max is at least as large as expectation with respect to distribution P. And if we take expectation of this guy with respect to P, this guy will be WP, and so this guy cancel. And FL is just distribution, so we just sum, and it is 1, so we get e to the power minus d max. Now, recall the performance of MWU algorithm I previously showed. So the left-hand side is average cost. The right-hand side is the cost of Y player's best strategy in hindsight plus some error term. And so here, as I explained in the previous slide, X player select XL as the argmax of this expectation. So each term can be lower bounded by e to the power minus d max. So left-hand side is bounded by 1 minus epsilon times e to the power minus d max. And then this holds for every y. And then we construct channel resolvability code as X player's strategy sequence from a sequence of X player's strategy. And then the WC constructed in this manner, we can rewrite this formula like this formula. Recall that the cost is this. Okay, so by plugging this into here and rewriting some manipulation, we can get this bound for every y. And so here we have some error term, and if we pick L sufficiently large as log L is larger than d max plus something, then this error term will be epsilon. And so we can rewrite this like this bound for every y. And so we get this bound. And even though we only have this bound, we can evaluate the total variation distance, and we can get bound. And for asymptotic setting, we have to do a little bit more complicated thing. So we construct channel resolvability code for each type class. So here T is a type, and for some input distribution P and T on each type class, we simulate some output distribution WP and T. And we introduced conditional typical set and pair of x and yn such that yn is included in conditional typical set. And also we introduced the typical set for output distribution. And also we consider some set of y such that the output distribution is not too small. We introduced these kind of things. And then we do some truncation. So we introduce this kind of set, and we truncate distribution outside of this set S. And then d max evaluated on this set S can be bounded by n times mutual information plus some error terms. And by adjusting these parameters, we can get the desired result. 5 minutes, okay, yes. And for general distribution, we first split distribution into type classes, and this type class distribution can be simulated by negligible randomness, and finally we can obtain the desired result. Okay. Let me conclude. So in this work, we have provided a deterministic construction for channel resolvability using MWU algorithm. This project is in a quite preliminary stage yet, and there are a lot of things to be done in future. So one thing is because matrix version of MWU is available, so we believe that our construction can be extended to CQ channel resolvability as well. And also, a very important thing is the smoothing part. We rely on typical set argument, and it is not one shot, so it is very important to derive nice one-shot bound that can be applied for general channel. And also another interesting direction will be construction of wiretap channel coding. And also if we can construct quantum wiretap channel coding, maybe that can be used to construct quantum channel coding. And also we can consider channel simulation, channel synthesis, etc. Thank you very much for listening.
Yeah, thank you very much for the very nice talk. Do we have any questions? Yes, Omar.
So do you know the complexity of finding the optimal channel resolvability code? So so you're given a channel and an input distribution, and you want to find the optimal subset that gives you the average, which is the closest. Is this NP hard or?
You mean complexity class?
Yes.
So this the size of channel resolvability code, this is exponential in the block length n, and this MW algorithm is iterative algorithm, and the number of round is the size of channel resolvability code. So it must be exponential. So this is a deterministic construction, but we do not claim this is a practical algorithm.
But let's say for a one-shot, just so the channel is given explicitly as a channel from d-dimensional to d-dimensional, let's say, and you want something which is polynomial in the dimension.
Dimension. Okay. Yeah, we have never thought about computational complexity, but so you're asking dimension complexity with respect to dimension of the channel. But so each iteration of MWU is not too heavy. So it's if the number of iteration is so I think the code book size of channel resolvability code will be in most channels. I think it will be proportional to dimension. So yeah, complexity should be proportional to dimension, I guess, but I'm not 100% sure.
Okay, thanks. Yeah, another question? Oh.
So it's you have mentioned the connection between resolvability and identification. And indeed, in your case where you study TMCs, it's known that deterministic identification gets you just exponential codes like this in resolvability, deterministic resolvability, you have found exponential codes. However, for continued channels, it's known that you can achieve super exponential codes for deterministic identification.
Yes.
Would you expect to find super exponential codes for channel resolvability in those cases?
So your question is?
So have you studied the channel resolvability over continuous channels?
Continuous channel, we haven't tried that. So the vanilla version of this bound, we have this log cardinality of output size. So this bound itself cannot be directly used for continuous channel, but maybe some other variant of MWU algorithm, for instance, this version. Then for such a version, instead of log dimension of output size, we can put some divergence term here. So maybe that version can be used for continuous case as well. But yeah. Yeah.
Or channels with continuous input and discrete output. Already applying here.
Oh yeah, input alphabet. Yeah, we can consider continuous case as well. Yes. Yeah. So maybe yeah, that might be interesting direction. And so for deterministic identification, channel resolvability is also useful.
I'm not sure.
Okay, maybe, yeah, but yeah, that's interesting direction. Yeah, so we will try to explore that. Thank you very much for the comment.
Okay, if there are no further questions, then let's thank Shun again.